So Ademir is actually the PhD student, myself. Victoria, which is lecturer at the University of New South Wales, and I'm a PhD student. So that's the summary of the presentation. And well, as I said, it's about advice for sampling odorous emissions at liquid surfaces. You all know there are a few of them. In the last conference in San Francisco, we presented work about flux chambers. We tried to simulate the fluid flow and mass transfer inside the flux chamber, and now we start doing that in the wind tunnel. So, as you know, there are problems with the aerodynamic inside the chambers and also inside the wind tunnel. So we're just trying with this technique to understand what's happening there and see if we can actually calculate the mass flow rate using this technique. So the idea, the first part of the work, so the idea was to simulate it in a very simple way. We just simplified and made assumption like it's a two-dimensional flow. So it's just the first results we are presenting here. This is the wind tunnel we are simulating, the one that has been developed at the University of New South Wales in the 90s. It's been used since then. And after it was first developed, there was some work to improve the features of it, so the inlet flow should be more uniform, so a buffer was added to the wind tunnel, and also some flat vanes, so to try to make sure that the flow was uniform at the inlet. So the representation for the numerical simulation that show right there in the picture, we just got the in the symmetry plane, we got the symmetry plane to simulate the flow. So as I said, it's a two-dimensional simulation. We assume that the flow is lambda. So it's a bit tricky because the Reynolds number and it's kind of in the transitional regime. So we could decrease velocity and also decrease or increase the velocity. So to be really sure it was lambda or to be really sure it's turbulent, there's a little bit of problem to simulate turbulent flows, but then we can do it as well. We assume that there was an isothermal condition, the flow is incompressible, and we assumed also a steady-state regime. So to simulate the flow using CFD, we have to solve these equations, which are straightforward equations: mass transfer, continuity, conservation of momentum, and the mass of the chemical species we are interested in. So we use this software, ANSYS CFX 13. And to solve that equation, of course, you know we have to have boundary conditions. And the boundary conditions are set like the inlet flow was uniform, and we tried to use a velocity as such to simulate the flow at the atmosphere. And there was a filter and inlet, so we assumed also the concentration 0. On the walls, we assumed non-flux and non-slip conditions. And the outlet, we assumed that there was no differential pressure, 0, and the concentration was, there was a constant gradient at the outlet for concentration. As for the water surface, which is more tricky in my point of view, we assumed that it was non-slip and there was no flux. By non-flux, we mean that there was no gas going into the liquid, but of course the gas coming out, that's what we want to simulate, gas coming out from the the liquid surface, but actually the actual boundary condition for the chemical species is that we assume a constant concentration. And this is something we just assume. We can measure the concentration of the liquid phase and assume it as constant, but it's I have to admit it's not yet a good approach. The better approach would be to simulate both phases, liquid and gas. But now we just simulate the gas phase, so we have to assume a concentration at the liquid surface. As you know, to run a numerical simulation, you have to test your mesh, unless you are doing large edge simulation, which is another thing. It's tricky to test the mesh there. So we did refine the mesh as much as we liked in order to see if the results would change with the mesh refinement. So it didn't. It didn't, or actually it did, but in a very small percentage. And so we could use any of the meshes actually, but we decided to go for the, this is, sorry, let me go back here. So this is velocity against the height inside the wind tunnel at distance from the inlet, 0.4 meters. So the different lines are different meshes we used, and you see visually there's no difference. But in numbers, the difference was really, really small. Here we did the same for concentration, because usually in numerical solutions you get easily mesh refinement and independence for velocity, for momentum equation, but for concentration equation sometimes you don't. So you have to check both of them, both variables. So we could choose any of the three. We decided to use the more difficult one, the largest mesh. And for all the simulations, we analyze the convergence, because then we know that we reached the last result. So after running the numerical simulation, you're not going to change the solution. So that's what the convergence test is there for. So we were certain about the mesh, and we were certain about the convergence. It means that we did the simulation correctly. It doesn't mean that we modeled it correctly. It means that the numerical simulation is correct. So then, to see if the model was correct, we said let's go and compare it with experimental data. So then we could see the model is correct. And then you see it's quite different. And then, of course, we blame the experiments, because the model is actually correct. I'm actually joking. We obviously presented it here because we think there are some problems with symmetry. It's because in the model you design it, it's very symmetric, and when it's actually manufactured, perhaps it's not symmetric, or the way you use it. So we think that's the reason why we got such different results. So we decided then to compare it with someone else, or something else, which was a theoretical model, which was, of course, closer to what we were trying to simulate. And then we use this classical solution, the largest classical solution for a fluid flow between two surfaces, and we get an algebraic solution. So we had something to compare with. And there you have, now when we compare to the theoretical model, it's an analytical solution. We see that it's okay, it's much closer to the analytical solution. So it means that it may not fit the experimental data, but it fits the theoretical solution. It means that we are doing the ideal configuration. We are not doing the actual configuration, but we are doing the ideal configuration, as I would say. And then we try to see, oh, sorry, it's a bit light there. We try to see the velocity profile we got, and then we realized that it's not a well-developed flow. So that brings us to the first thing I said about the Reynolds number. So we have to try to get away from the velocity we use. We have either to increase the velocity or to decrease the velocity. We show that we are really laminar or really turbulent. And then because the section is not very long, so the flow is not well developed. That's why we have difference between this analytical solution and the numerical results. So we try to look at the literature. People they found the same kind of problems, and yes, we found some people reporting in the same kind of situation that they think that's not well developed. The flow is not well developed in the wind tunnel. It suggests that perhaps it should be a little longer. We want it to be portable, so we have to see and to compromise. So that's the experimental data I was talking about. We looked at the literature and we found that people also got similar results to what we got. So we were, okay, that must be the reason for that. It's not well developed. But on the other hand, even though the velocity profile showed it was not well developed, and we calculate the mass transfer coefficient, and we use ammonia for that. We tried that with ammonia. We could try it with some other substance. We decided to do it with ammonia because we want something that was important in the gas phase. So we compared the three numbers given by the classical Blasius solution. Some experimental work that has been done before with the same wind tunnel and the CFD simulations, and those are the results, the difference we got. And this slightly higher value of mass transfer coefficient, it can be explained because we got higher velocity and thinner boundary layers. I showed that before there. You see there? So it's a little bit thinner boundary layer. So that's very much consistent with the larger mass transfer coefficient. So we tried to evaluate the concentration distribution inside the wind tunnel. Again, it's in the symmetry plane. And we found that the concentration at the outlet, it's not uniform. I would like it to be because of the measurements, but it's not. So we have a very intense gradient close to the surface, to the liquid surface. Well, that's what I was saying before. Even though a baffle and veins were used in terms of the wind tunnel, it's not yet made the wind profile, the velocity profile uniform at the inlet, and we still get a lot of concentration gradients, strong concentration gradients at the inlet. So in conclusion, we found it hard to find experimental data to validate the simulation, because actually what we'd like to have is a velocity profile inside the wind tunnel and the concentration profile, so it would give us data enough so to be sure about the model we are proposing. We compared, as I told you, the theoretical model of blazes for the laminar boundary layer, but it indicated that we are modeling more the ideal situation, as I said, than the actual wind tunnel, because I showed you it lights deviated from blazes formulation. And the experimental data we had, it showed that the velocity profile was not fit the well-developed flow inside the chamber, inside the wind tunnel. So it was consistent with what we found. Even though the flow was not developed as I thought it would be, we found the mass transfer coefficient within the previous measurements and within the blazes theoretical solution. So it was a small error. And we also, as I pointed out before, the concentration distribution at the outlet tube was highly non-uniform. So that's the first step in the work, and now we are trying to set experiments to get experimental data to actually validate the model. That's what we have to do there now, because the previous experimental data we have is not enough for us to validate the model. We have to study the side, the wall and the side, how it affects the fluid flow inside. So I guess the next right thing to do is to do it in 3 dimensions, because the computer power we have today, it's pretty much easy to do a 3-dimensional simulation. We have to shift from laminar to turbulent if you want to keep the wind speed, the wind velocity inside the tunnel. But actually we have to check, the most important parameter is not actually the speed, is the friction velocity on the liquid surface. That's what we have to bear in mind. So to simulate the real flow in the atmosphere. And we have to investigate. Okay, and we have to investigate the necessary length for reaching out that outflow. So to see if we can, by increasing a little bit the wind tunnel, we get a well-developed flow. So the main idea is to get the wind tunnel operating in situations that we know very well what it is. You know, if we can. Because by modeling it means that we know well how it works inside the wind tunnel. So we have to change both, to change the wind tunnel, how it is designed, so to match the model and be able to model whatever is happening inside the wind tunnel. So it's like both ways working together. So this is Ademir, the PhD student, working under the supervision of Richard, and we'll be seeing him, I'm sure, in the next Odorous conference. And just abuse here, just a Brazilian and Australian collaboration starting.
Thank you. Got time for one question? Yeah, Franz? You're the first on the right.
Thanks very much. Very nice to see this old box, which is 20 years old again. And of course, Richard would have been expected at least that I would have to comment on that. If you carefully read the original publication, you will find, and I have it here with me, and I can cite it. In the study, we found that the sensitivity of the anemometer available for measuring the velocity profiles limited the minimum air velocity to about 0.33 meter per second. So this was only an instrumental point of view. In 2000, what was Singapore? 2001, where I couldn't attend due to health reasons, one of my colleagues presented our measurements. We measure with the laser instrument that can measure down to 0 meters per second. So this is always important. And generally, say the lower the mean velocity, the better the aerodynamic performance. And there's one very important point.
You mean it's Lana?
Sorry?
By saying that it's better aerodynamic performance, you mean it's
I
Lana?
don't, we can discuss it later, but that's one important point. If you operate with high speeds, you will get a high dilution. If you work on surfaces that have a relatively low emission, you will find that the odor concentration at the outlet is close to 0. And for this reason, it is very important how olfactometric laboratories handle the sample where they cannot measure anything. If they, for example, say, well, we cannot measure anything, it must be below 20 odor units, 10 odor units per cubic meter, then the next guy who operates with this value says, okay, I don't know anything, but I know it's below 10, so let's take 10 and multiply it with the surface. This gives a really big emission at a space where possibly you don't even have any emissions. So this is an important point. And the second point is, if you look for atmospheric dispersion situations, the most important ones, by a factor of 20 to 40, are those with very, very low wind speeds, or even no wind speed. This gives the longest traveling distance. So we will never be able to measure true odor, we will never be able to measure true emission factor, but keep in mind these two facts, that you have a long distance of traveling with very, very low things. And if you need more data, we have made a lot of measurement with this laser installation, so we can exchange that. Thanks.
Yeah, just to point out that actually the most important parameter is not the velocity itself, but it's the friction velocity. That's what we have to calculate and to be sure that we get inside the wind tunnel, so to simulate the atmosphere.
Coffee time.
Yes, one second. There are two possibilities. If we have this laminar thing, you can either mix inside the hood, or you can make a total sampling and mix inside the sample bag. So these are the options.
Thank you, Frank. Thank you, Jane.